This is the second presentation in the series of lectures on circuit simulation and device modeling. In the previous presentation, I have explained how to construct circuit equations with linear circuit elements and how SPIKE solves the circuit equations. In this presentation, I will go over how SPIKE performs DC simulations for nonlinear circuits. To begin with, I will use an example to illustrate the process. In this circuit, there are two nonlinear resistors, of which the current is some function of the voltage across it. We denote the functions to be I2 and I4. I use a diode symbol to indicate the nonlinear resistor to make them look more familiar to you. In fact, diodes are really nonlinear resistors. You can just imagine I2 and I4 to be the common diode equation if that will help you to visualize the process better. Following the steps of the modified nodal analysis to solve the circuit, we first write the KCL. As there are only two nodes, excluding the ground, there are only two node equations. We then rewrite the KCL using the branch equations to express the branch currents in terms of branch voltages. Please note that even though I2 and I4 are still there, they are actually expressed in terms of branch voltages already. It is just that I2 and I4 are nonlinear functions, that they are not as simple as a constant multiplied by a voltage. As all branch currents can be expressed in terms of branch voltages, we can skip step 3, as there is no need to add additional branch equations to the system. After that, we follow step 4 in the modified nodal analysis to use KVL to replace the branch voltages with the node voltages. But this system of equations have nonlinear components that cannot be expressed as a constant times a voltage. Therefore, they cannot be directly entered into the Jacobian matrix as what we did before. We have to find a more general way to solve this set of equations. To do that, we first express all currents leaving a node to be a function. Here, I1 is the total currents leaving node 1, and I2 is the total currents leaving node 2. The independent variables of both functions are the node voltages. We can collect all node voltages and put them into vector form. We can also collect all the total currents leaving a node and form a current vector as shown here. As all the elements in the current vectors are dependent on the node voltages, the current vector can simply be represented by a more compact form of I as a function of V. Then, the previous equations after KVL can be written as the current vectors must be equal to 0. That is, the goal of the simulator is to solve for the node voltages that results in 0 total node currents leaving any nodes. As the function I of V equal to 0 can be any nonlinear function, the solution may not be expressible by an analytical equation. To find a general solution to the system of equations, an iterative approach will be used to solve for a numerical solution. And the Newton-Raphson method is commonly used to find the numerical values of the voltage vector V. Let's spend some time to understand the Newton-Raphson method. It is easier to illustrate the process in 1D, and then extend the concept to multi-dimensions. For a single variable function of current in terms of voltage, we can perform Taylor expansion over a point V0. It results in the following expression. We only keep the constant and linear terms and ignore all the higher order terms. Physically, it means we use a linear function to approximate the original function at the point V0. It will predict the solution of I equal to 0 to happen at V equal to V1. Obviously, It is not correct, but it is closer to the solution. So we further use V1 as a guess and expand the function around it. It will be a better approximation around the solution. The process continues, and each guess will be closer to the solution. Going back to the equation, we can solve for the next guess by equating the approximate equation to 0 when the current guess V0 is given. In the example, V1 is given by the equation here. More generally, the equation to find the next solution at the k plus 1th iteration, given the voltage value at the kth iteration, is expressed by the equation here. Physically, the derivative provides a guide on the direction and step size to make the next guess. I would like to make a remark that the derivative mainly affects the convergence of the iteration, but not the accuracy. It is possible that an incorrect derivative can result in better convergence if you are lucky enough. That is, the wrong derivative may guide you to a point closer to the solution, and thus converge faster. But we should not rely on it. In vector form, the iterative equation is similar, with the scalar variables replaced by vector variables. The same concept is still valid, and the multidimensional derivative serves as a guide to which direction to search for the next solution. Multiplying out the equation to remove the fraction, it can be written in the form given here. The derivatives of a vector function with respect to a vector variable gives a matrix. When the equation here is expanded out to show the individual elements, it looks like the following. The matrix that represents the derivatives of the current with respect to voltage has a unit of conductance. It is actually the same Jacobian matrix that we learned before in the first presentation. Let's go back to the example circuit. The functions of total node currents as a function of node voltages are repeated here. Following the iteration process, the matrix equation for iteration is given here. While it looks complicated, the right-hand side of the equations are all evaluated at the kth iterations, with all the vk's given. So their values can be calculated quite easily. Actually, many terms on the right-hand side of the equations cancel out each other, and it can be simplified to what is shown here. But we will generally refer to the form above it, because it is a more universal way to calculate the required values. It should be noted that all the terms from the linear elements disappeared on the right-hand side of the equations. It is also true for I2 and I4 if they are linear elements. In such a case, the equation expressed as voltage time derivatives is exactly the same as the first current term. So the two terms cancel out each other. To summarize, the final matrix equations of the example circuit is given here. Unlike the case for linear circuits, this equation will be solved iteratively until all the total node currents become 0. The condition for convergence is given by the vector equation here. The top row represents all currents to node 1, and the second row represents the total current to node 2. We want them both 0. And this can be also achieved by checking the values of voltage in the new guess compared with the current guess, which is given by the equation here. We can also directly assemble the circuit equations from the circuit elements. Notice that the entries from the linear elements are the same as what we covered before. So we can use the same matrix stamp to enter them into the Jacobian matrix and the right-hand side of the equations. For two-terminal nonlinear circuit element given by the figure here, the matrix entries are given here. Again, while the right-hand side of the equation looks very complicated, it can be evaluated directly by a computer. We can also represent the matrix stem of the nonlinear element with an equivalent circuit that only composed of linear elements. For the nonlinear resistor used in our example, the equivalent circuit is shown here. The values of the conductance and voltage control current source is given by the following equations. If you follow the procedures to compose the matrix equation using the matrix stems for the linear circuit elements, you will find that the resulting matrix is the same as what we have before in the previous page. But we should pay attention that the values of the equivalent conductance and voltage control current source will be changing at each iteration. As a real example, we can use the diode equations to construct the diode model. The diode equation is given here. Based on this equation, the equivalent conductance and the current of the voltage control current source are given here. These values can be directly entered to the Jacobian matrix representing the circuit. So far, we have been working with two-terminal devices. But many active devices, such as BJTs and MOSFETs, have more than two terminals. We will describe how to handle multiple terminal devices here. Consider a general N-terminal device with terminal voltage V1 to Vn and terminal currents I1 to In. The general topology can be represented by the following symbol. We have to define the polarity of the current directions, and we will define the currents going into the device as positive. Then, the contribution of this device to the circuit matrix that is already constructed by other circuit elements is given here. The approach is exactly the same as that of a two-terminal device. You can provide it by writing the circuit equations and perform the modified nodal analysis as we described before. But we will skip it here as the process is very mechanical and boring. We will end this presentation by a real example. Assume you have a MOSFET with the drain current given by the equation used in many textbooks here. To simplify the explanation, we will just consider the equation in the linear region. Then, the derivatives of I1 with respect to the three terminal voltages are given here. As I2 is just the negative of I1, its derivatives are also the negative values of what that is already calculated for I1. As the gate is regarded as an insulator, its current is assumed to be zero under all bias conditions. So, all its derivatives will be zero. Then, the matrix entries of a MOSFET will be what is given here. We can also represent the MOSFET with a linear equivalent circuit that generates the same matrix entries. The linearized circuit is shown here. You should pay some attention to the matrix as the MOSFET generates all zero entries to the gate node of the matrix. It may result in a singular Jacobian matrix. To avoid singularity, the gate terminal has to be connected to some other circuit elements to generate some non-zero entries to the equation representing the gate node in the circuit equations. As a summary, we have added nonlinear devices with more than two terminals to our collection of elements for circuit construction. Unlike linear circuits, nonlinear circuits require iterations to solve for the solution, and it may result in non-convergent problems. As the convergence rate is subject to the quadratic convergence of the Newton-Raphson method, some fast-changing current with respect to voltage, such as exponential function, can create non-convergent problems if not handled carefully. We will deal with the non-convergent problems later. In the next presentation, we will describe how to add time-dependent circuit elements, such as capacitors, first.